dou r square times dou t by dou r plus kg by k is equal to 1 by alpha dou t by dou t. So this is the equation for the cylindrical one-dimensional heat flow for the case of spherical coordinate system. Sorry, I said cylindrical, it is spherical. It is getting mixed up while teaching. Excuse me for that. So next we will see the concept of thermal resistance, that when we can apply that, and concept of thermal resistance is very powerful technique in the heat transfer analysis, and it can be used in variety of problems, and it can give you the first cut approximation of any heat transfer problem. Okay, so let's start with that concept of thermal resistance. As there is a electrical resistance in the case of electricity, there is similar analogy in the case of heat transfer. There are a lot of analogies between electrical and heat transfer problems. In heat transfer and fluid mechanics problems, we will see along the way. So the first thing is, this concept is used for the solving of composite layer problems. This concept is used for solving composite layer problems. Like we see that in the window of a car there is a glass pane, double glass panes. So one glass pane, then followed by the vacuum, and then again glass pane. So that is the example of a composite layer problem. Okay, similarly in the walls we have first the cement, then brick, and again cement. So that is also a composite layer problem, and that bricks in the complete wall are arranged in parallel fashion, right, for the heat flow. So we can think of such problems. Then we have to see that what are the valid means when it is valid, when the concept of thermal resistance is valid. So it is only valid in case of steady state heat transfer when there is no heat generation, no internal heat generation within the body, each body, right? So valid only when there is steady state condition and no internal heat generation. Okay, so now let's start with the analysis of it. I was giving the analogy to you about the electrical and thermoconductor. So we know that electrical conductor, let's compare it, and thermal conductor. Let's suppose it is a wire, and let's suppose it is cylinder. Temperature difference is maintained along its two cross-sectional areas and heat is flowing through it. Q amount is the rate of heat that is flowing. So in the electrical case, there is current is flowing when there is potential difference. Okay, so current is flowing because of potential gradient, and according to Ohm's law, I is delta V by R. So that is electrical resistance, which is provided by the electrical conductor. Similarly, in the heat transfer, there is temperature difference analogous to potential difference, and there is thermal resistance analogous to electrical resistance, RTH. Okay, so we can draw the thermal network like this for this simple thermal conductor T1 and T2, and this is the thermal. Okay, so this thermal conductor can be equivalent to this. Okay, so from here we can write like this. So thermal resistance is nothing but delta T by Q. So its unit will be Kelvin or degree Celsius by watt. Always remember that change in temperature is same in degree Celsius as well as in Kelvin. You take in degree Celsius, I'm not talking about temperature, I'm just saying the difference of temperature. Difference of temperature, whether you take in degree Celsius or Kelvin, it will be same. Okay. For example, 100 degrees Celsius and 0 degrees Celsius. Both are temperatures, and let's say 373 Kelvin, 273 Kelvin. Temperature difference is 100, and here temperature difference is 100 degrees Celsius. The temperatures are different, but change in temperature is same. That's why we can put the unit as Kelvin or degree Celsius here, or degree Celsius by watt. Okay, let's now think about the series and parallel problems in case of heat transfer. In case of series problem, consider there are two bricks, two plain walls or are placed side by side. Okay, and heat is flowing in this direction, and there is temperature of T1 here, temperature of T3 here, and some temperature of T2 here. For heat to transfer, there must be a temperature drop. We don't know how temperature profile is in there from T1 to T2. That's why I am drawing just dotted lines. Okay, don't think it is linear always. It depends. And these are two materials, 1 and 2. Let's draw a simple network of this. And since there is no heat generation inside both the material 1 and material 2, and there is steady state heat transfer, these are two assumptions I am making in this problem. And so T1 is this wall temperature at every point along the y direction. There is T1 temperature only, and here interface T2, then second material, and then T3. So that's the temperature, and heat is flowing in this direction. Okay, we can see that heat is flowing from T1 to T2 and then to T3. So overall we can write like this: heat flow T1 minus T3, overall temperature difference divided by, in series heat will be same, therefore resistance will add. So let's say first wall will offer the resistance of R1 and second wall offers the thermal resistance of R2. So R1 plus R2, easy. So it was just a basic problem. Now let's talk about the parallel problem when the two materials are in parallel, like bricks. Okay. Let's say that these two bodies are placed like this and they are in perfect contact. I will explain what is the meaning of perfect contact. And heat is flowing like this. So when heat is flowing like that way, it can have choice of two paths. Some amount of it can go by the upper path and some amount of it can go to the lower path. So heat is dividing, it is not same, so it is in parallel connection. We can identify like this. And let's suppose it is maintained temperature T1, it is maintained temperature T2, these two walls. Okay, we don't know. Okay, so we can draw the equivalent circuit like T1, T2. Okay, these all points will be at T1, these all points will be at T2, and first material offers resistance of thermal resistance of R1, second material offers thermal resistance of R2, and since it is in parallel, we can find the equivalent resistance of it, T1 in between T1 and T2, Rp. So we know in parallel 1 by of Rp is equal to 1 by of R1, 1 by R2. Okay, so we can find the heat flow rate as T1 minus T2 if T1 is higher divided by Rp. Okay, this is the problem of parallel case. In I means here I mentioned that there is perfect contact. What is the meaning of perfect contact? I will explain now that why I mentioned about that. We can write it as a note. In practical cases,